What if the universe isn't what you think it is? Not a void filled with stars, not an endless playground of matter and energy, but something colder, quieter, and far more calculating. Imagine that everything around you, the screen you're staring at, the neurons firing in your brain, even the laws of physics, is just the result of a process. Not a cosmic accident, but a computation. Not a simulation, not exactly, but something deeper, something realer than that. A process that doesn't pretend to be a universe, but is the universe. A quantum computer that has been running for 13.8 billion years. One where every collision between particles is a calculation. Every moment in time is a step in the algorithm. Some physicists don't just entertain this idea, they believe it. That the universe is processing information, just like a quantum computer, constantly updating itself, evolving, crunching unimaginable amounts of data every second, and turning it into reality as we know it. And if that's true, then you are not just made of atoms, you're made of instructions. You are part of the output. If this mind-bending idea sparks your curiosity, consider hitting that subscribe button for more deep dives into the universe's biggest mysteries here at Stellify Science. Stellify Science dives deep into cosmic mysteries. If you find this fascinating, hit the like button, share your thoughts, and subscribe to keep exploring with us. We've been taught to look at the universe like it's a physical machine, a collection of objects, atoms, molecules, planets, moving through space, pushed and pulled by forces, obeying laws. Drop a ball, it falls. Light a match, it burns. Everything from the smallest electron to the largest galaxy behaves in predictable, measurable ways. But beneath all of that motion, beneath the matter and energy, there's a growing belief among physicists and computer scientists that something else might be hiding, something more fundamental, information. It doesn't sound very physical at first, but in physics, information isn't just a label or a number stored on a hard drive. It's real. It can be measured. It can't be destroyed. When something happens in the universe, a particle changes direction, a quantum state collapses, a star explodes, there's a change in information, and that change has consequences. That's why some physicists now believe that information is just as real as matter or energy, maybe even more so. John Wheeler, who worked closely with Einstein and helped lay the groundwork for quantum mechanics and general relativity, once summed it up in 3 simple words: it from bit. What he meant was this: every particle, every force, every field, everything we call reality might ultimately emerge from simple yes or no questions. Bits. The same kind of bits your computer uses, only woven into the very fabric of space and time. This isn't a metaphor, it's a serious proposal. Think about how digital systems work. You have a set of rules, code, that processes inputs and produces outputs. In computers, this happens through logic gates. But in the universe, it happens through physics. The equations that describe gravity, electromagnetism, quantum mechanics. They don't describe objects. They describe how the properties of things relate to each other over time. When a photon hits your eye, it carries information. Its energy, its direction, its polarization, all of that gets translated by your body into electrical signals, then into thoughts. And where did the photon get its information from? The atom that emitted it, and so on, back through time. Every interaction is a transmission of data. Every force is a way of transferring information. Even what we call mass or charge might just be labels for how an object stores and processes information. Now imagine zooming all the way down to the smallest possible scale. Not atoms, not electrons, down to the Planck scale, where space and time start to break down. At this level, some physicists, like Carlo Rovelli, think space isn't smooth and continuous, but granular, discrete. Instead of being an empty stage that things move through, space itself might be made up of tiny, indivisible units, like pixels on a screen. And time, instead of flowing smoothly, might tick forward in small jumps, like frames in a film. If we closely observe the world around us, it becomes evident that reality is far more discrete than continuous. Everything appears to follow an algorithmic structure. In fact, quite counterintuitively, the universe seems to lend itself more naturally to digital representation than to analog. Consider DNA. It's essentially a sequence, a biological code, a set of instructions for building life in all its forms. Plants, insects, fish, animals, and humans. At a deeper level, elementary particles themselves are not only discrete in nature, but also express their fundamental properties, such as energy, in quantized form. When we strip it all down, the underlying fabric of everything appears to be governed by the binary, a cosmic code of zeros and ones. If that's true, then the universe doesn't just look like a digital system, it is one. In this view, the laws of physics aren't just things we discovered. They're the source code of the universe. And everything we see, galaxies, planets, life, is just what happens when those rules run long enough. There's another strange implication here. If reality is digital, then it's finite. It can only contain a limited amount of information. There's only so much data you can pack into a given volume of space before it collapses into a black hole. That's not a guess. It's a well-known principle in theoretical physics called the Bekenstein bound, proposed by Jacob Bekenstein. It suggests that the maximum amount of information you can store in a region of space isn't based on its volume. It's based on its surface area, which is exactly what we see with black holes. In fact, black holes are some of the best evidence we have that reality is, at its core, informational. According to the famous holographic principle, the information inside a black hole isn't lost. It's encoded on its surface. Just like a 3D image can be stored on a 2D hologram, the entire universe might work the same way. What we see as three-dimensional space could actually be a projection of data encoded on a distant boundary we can't see. But even if the universe isn't literally holographic, the idea that it's fundamentally made of information is hard to escape. It explains too much. Why the laws of physics are so clean. Why quantum states collapse in specific ways. Why the speed of light is the maximum rate that information can travel. It all fits. The universe, it seems, might not be a place where information lives. It might be information living. The simulation theory is related but different. It suggests that reality is an artificial construct running on a computer built by someone else. But what we're talking about here is subtler. There is no outside, no other system. The universe is not on a computer. It is the computer. It is the thing performing the computation. It doesn't need anyone watching it. It doesn't need a server farm or a control panel. It simply is what it is, a system that processes information according to its own rules. In other words, when we talk about the universe as a quantum computer, we're not saying it's pretending to be real. We're saying this is what real is. This perspective doesn't change the world you see around you. You'll still wake up, make coffee, go to work. But beneath it all, the particles in your brain are interacting with each other in ways that carry meaning. And those interactions aren't just chemical, they're informational. That means your thoughts, your choices, your experiences, all of it is built from bits. The same kind of bits that describe the orbit of a planet or the decay of a neutron. You are the output of a process, but not in the way people usually mean. You're not a puppet. You're not fake. You're just real in a way we're only beginning to understand. If we're going to ask whether the universe is a quantum computer, we should probably understand what a quantum computer actually is. Not the headlines you've seen, not just a faster computer or a futuristic machine that solves hard problems. That's part of the story, but it's not the point. The real story is about how quantum computers process information and how that process is completely unlike anything we've ever built before. Let's start simple. A normal computer, the kind you're probably using right now, works using bits. A bit can be either 0 or 1. That's it. Everything your phone or laptop does comes down to millions or billions of these bits, flipping between two states. Turned on or off, yes or no. This system works because it's simple, stable, and predictable, but it has limits. Some problems are just too complex for classical computers to solve in a reasonable time. That's where quantum computing comes in. A quantum computer uses qubits, not bits. And qubits don't behave like tiny switches. They behave like quantum systems, which means they can do some very strange things. For one, qubits can be in a state called superposition. That means they aren't just 0 or 1. They can be in a combination of both at once. Think of a coin spinning in the air. It's not heads or tails. It's kind of both until you catch it. In quantum mechanics, this isn't just a metaphor, it's real. A qubit can represent multiple states at once, and when you have multiple qubits working together, the number of possible states grows exponentially. 10 classical bits can represent one of 1024 possible values, but 10 qubits, they can represent all the 24 values at the same time. This gives quantum computers an insane level of parallelism. They're not just trying one solution after another. They're exploring many at once. Then there's entanglement. When two qubits become entangled, the state of one instantly affects the state of the other, no matter how far apart they are. That's not a sci-fi concept. It's been tested over and over in experiments. Einstein called it spooky action at a distance, and it still bothers people today. But it's real, and it's a key part of how quantum computers work. Entanglement allows qubits to work together in ways that classical bits can't. They don't just store information, they share it across space. This enables computations that are massively more efficient than anything classical systems can achieve. But it's also fragile. Quantum systems are notoriously sensitive to their environment. Any disturbance, noise, heat, observation can destroy the superposition or break the entanglement. That's why building a useful quantum computer is so hard. You need to isolate your qubits, control them perfectly, and keep them stable long enough to run your algorithm. We're getting better at this, but we're still at the early stages. So that's the basic picture. Quantum computers use superposition and entanglement to perform calculations that would be impossible or impractical for classical machines. But what does this have to do with the universe? Well, let's go back to the fundamentals of quantum mechanics. At the microscopic level, everything behaves like a quantum system. Particles don't have definite positions or velocities until we measure them. Instead, they exist in a spread of probabilities, a kind of quantum blur. And when they interact, they don't just bump into each other like billiard balls. They interfere, they entangle, they collapse, they compute. And that's the key idea. A quantum computer doesn't simulate quantum mechanics. It is quantum mechanics. It doesn't fake the rules, it runs on them. That's why quantum computers are so powerful, because the universe itself is quantum. So when you build a quantum computer, you're not building a model of reality. You're building a machine that plays by the same rules reality already follows. This is why the idea of a quantum universe is gaining traction. Not because it's convenient or trendy, but because it might explain why the laws of physics look the way they do. Why reality has structure. Why events follow patterns. Why entropy increases. Why time moves forward. All of these features, information flow, state changes, probabilistic outcomes, are features of computation. So the question isn't, could the universe be a quantum computer? The real question is, what else could it be? It's one thing to say, maybe the universe is a quantum computer. It's another to look at the science and find signs that this might actually be true. This part isn't about speculation or metaphors. It's about models, theories, and real work by physicists that give this idea some serious traction. Let's start with something strange that's been puzzling physicists for decades. The black hole information paradox. This problem first came up when Stephen Hawking showed that black holes aren't entirely black. They slowly evaporate by releasing what's now called Hawking radiation. But here's the issue. The radiation seems to be random. If a black hole completely evaporates and all that's left is this radiation, then what happens to the information that fell into it? Quantum mechanics says information can't just vanish. It's one of the core rules. So if black holes destroy information, that breaks the laws of quantum mechanics. But if they don't, where does the information go? This is where the quantum computing perspective comes in. A black hole, some researchers argue, might be acting like a quantum informational processor, not a metaphorical one, an actual quantum system that encodes and scrambles information, but doesn't erase it. When the black hole evaporates, it doesn't destroy the data. It releases it, just in a highly scrambled form. In fact, some physicists now think black holes are the fastest scramblers of quantum information in the universe. The physics of black holes, one of the most extreme places in nature, might only make sense if we treat them as quantum computers. And it's not just black holes. More and more researchers are pointing to quantum entanglement as the glue holding everything together. Some theories now suggest that space-time itself emerges from patterns of entanglement. A leading researcher exploring how space-time emerges from quantum entanglement is Mark van Ramsdonk. His influential work, particularly his 2010 paper, Building Up Space-Time with Quantum Entanglement, argues that the connectivity of space-time is intimately tied to the entanglement of quantum degrees of freedom, with disentanglement causing regions to separate. This has been pivotal in advancing the idea that entanglement is the glue underlying space-time structure. The idea is that space isn't fundamental. It's built from quantum bits that are entangled in specific ways. If the entanglement changes, the geometry changes. Think of it like stitching together a fabric. The more tightly things are stitched, the closer they appear in space. Tear those stitches, and the space between them grows. This view flips everything. Instead of space containing information, information builds space. This model isn't just poetic. It's being tested in real calculations. Tensor networks, like MERA, multi-scale entanglement renormalization ansatz, are mathematical tools physicists use to describe entanglement structures. When you build a system using MERA, you don't just get information, you get a geometry that looks like curved space. It's a hint that quantum computations don't happen inside space-time. Space-time might emerge as a result of those computations. Another area pushing this idea forward is quantum error correction. In quantum computing, error correction is the key to making reliable calculations. Qubits are delicate. They can easily lose their quantum state, if not protected, as we discussed before. But clever error-correcting codes can preserve information by spreading it across multiple qubits. Physicists are starting to find deep connections between quantum error correction and the structure of spacetime. Some models of AD-CFT correspondence, for instance, can be described as quantum error correcting codes. This suggests that the universe itself might be using similar codes to preserve its information. Every region of space contains quantum information. This information is not stored in one place, but is spread out through entanglement. Even if some parts get corrupted, like near a black hole or due to quantum fluctuations, the overall information is protected by a code, like a cosmic firewall. That code is essentially a quantum error correcting code. In other words, space-time geometry might literally be a quantum error correction system, a way for the universe to compute without breaking down. And let's not forget the weirdness of quantum mechanics itself. Every time we run an experiment with entangled particles, every time we see interference patterns in a double-slit test, we're watching information behave in ways that only make sense if something deeper is being processed. The rules of quantum physics, superposition, measurement, entanglement, aren't just oddities. They're the exact same rules that power quantum computers. Scientists are already building small versions of them in the lab. And the more we understand how they work, the more the universe starts to look like a scaled-up version of that same logic. So we have black holes acting like scramblers. We have the holographic principle compressing information across boundaries. We have space-time emerging from entanglement. And we have quantum error correction showing up in our models of reality. These aren't coincidences. They're pieces of a puzzle. The pieces don't give us a full picture yet, but they point in a clear direction. The universe processes information, not by accident, but as its basic function. And if it processes quantum information using the rules of quantum logic, then it's fair to ask whether it qualifies not just metaphorically, but literally as a quantum computer. Of course, this view still faces challenges. We don't yet have a full theory that combines quantum mechanics and gravity. We don't fully understand how space-time and computation relate on large scales, but the clues are piling up. And the more we look, the more it seems like the things we thought were solid, particles, space, time, are just the output of something more fundamental: information, logic, computation. Not in the background, but as the thing itself. If the universe is a quantum computer, then the way we've been thinking about physical laws might be incomplete. Not wrong, but backwards. Instead of the universe obeying fixed laws like a machine follows instructions, the laws themselves might be a product of the computation. Not external rules, but internal logic. That means we shouldn't think of gravity, electromagnetism, or the strong and weak nuclear forces as separate pieces of machinery. Instead, they could be different layers of processing, subsystems of a larger algorithm. Maybe they only appear distinct because we're zoomed in too far, like looking at a screen and seeing pixels, rather than the full image they form. So, here's one way to see it. What we call laws of nature are just the rules that remain consistent across the most stable, long-running parts of the computation. They're emergent, not imposed. And if that's true, then some laws might not be absolute at all. They might shift under the right conditions, say in the early universe, or near black holes, or at the edge of the observable cosmos. They might even be different in other regions of a much larger, connected quantum system. Call it a multiverse, if you like. Though this isn't about parallel Earths, it's about different parts of a wider informational structure running different versions of the rulebook. This also changes how we understand energy. Traditionally, energy is a property of physical systems, the ability to do work, to move matter, to cause change. But in information theory, energy isn't just fuel. It's tightly linked to how information can be stored, transmitted, or erased. Erasing a bit of information requires energy. Processing information consumes energy. If the universe is doing this constantly, then maybe the Big Bang wasn't the birth of matter in space. Maybe it was the boot-up event, a surge of usable energy that made large-scale quantum processing possible. That gives a different meaning to thermodynamics. The second law, that entropy always increases, might just be a statement about the universe exploring more and more configurations of information over time. Not because things are getting more chaotic, but because the system is expanding its state space. It's processing more, storing more, evolving through more possibilities. In other words, the universe is moving towards states with greater and greater information content. What seems to us a disorder is simply information not yet understood. And that brings up a question. What is the purpose of this computation? Not in the mystical sense, not why are we here, but in the scientific sense. Is the system optimizing for something? Is it computing toward a goal? In typical computers, we write programs to solve problems. But in nature, the problem might be open-ended. Maybe the universe isn't solving anything. Maybe it's just running, exploring the full range of outcomes possible under its rules. Or maybe it's biased toward complexity, not by design, but by statistical tendency. From the formation of atoms to the rise of consciousness, complexity emerges because the universe's way of processing information favors interaction, feedback, and self-organization. Even within the bounds of entropy, structure doesn't just survive, it thrives. It's not that the universe intends complexity, but that complexity is what reliably unfolds when information flows through a system governed by consistent rules over time. Think about it. Over billions of years, the universe has gone from a hot, simple state to one filled with complexity. Atoms formed, then stars, then molecules, life, and eventually consciousness. Not randomly, but through a slow accumulation of structure and order. This doesn't break the rules of entropy. It works within them. But it shows that complexity can emerge naturally in an information-rich system. Could it be that the universe's computation leans toward maximizing complexity? Not as a goal, but as a statistical result of how information is processed. If so, then life, thought, intelligence? None of this is an accident. It's what tends to emerge in this kind of system. Not because it's meant to, but because these outcomes are inevitable when enough information flows through enough steps. They're patterns that appear again and again in a system that favors interaction, feedback, and growth. That also reframes our place in the system. We're not separate observers watching a cosmic machine tick along. We're made of the same informational processes. Our thoughts are just as much a product of quantum interactions as gravity or magnetism. But we're unusual in one sense. We're part of the system that can reflect on itself. Our awareness, however you define it, is one of the few known structures that can model the rules that created it. That might be the rarest thing in the universe. Not life, not intelligence, but self-reference. The ability of a process to loop back and understand the very system it belongs to. In a classical universe, that might seem impossible. But in a quantum computational one, it's not surprising at all. Recursive systems happen all the time in computing. Programs that write programs, systems that model themselves. Maybe what we call science is just the universe's way of iterating on itself, testing, refining, revealing its own logic through minds embedded inside the very process they're studying. So what would it mean if the universe is a quantum computer? It means we're not observing the machine from the outside. We are the machine studying itself, line by line, bit by bit. Once you start thinking of the universe as a quantum computer, a question inevitably comes up. If this is all computation, then could we simulate it ourselves? Could we build a machine inside the universe that fully mirrors the universe? It sounds simple at first. After all, we already build models. Physicists simulate galaxies, black holes, atoms. We use equations to recreate how particles interact or how stars evolve. With quantum computers advancing, we're beginning to simulate quantum systems too. Small ones, but still accurate. So if the universe is running on a quantum engine, then why not build one of our own? One that mirrors the entire thing. But here's the catch. Simulating a system from within the system you're trying to simulate isn't straightforward. There are hard limits, not just in technology, but in physics. To start, there's a basic principle from computer science. No machine can perfectly simulate itself with full detail and precision. This isn't philosophical, it's mathematical. If you try to build a perfect model of something as large and complex as the system you're in, the model will require as much or more memory and processing power than the original. And since your model exists within the system, it can't exceed the system's total capacity. This is sometimes called a reflexive limitation, the inability of a system to fully map or understand itself without loss. A mirror can't reflect itself. A book can't contain a perfect copy of itself inside its own pages. And in physics, this idea appears in more than just logic. It shows up in thermodynamics, in limits on information density, and in quantum theory itself. For instance, think about the Bekenstein bound again. The idea that any region of space can only hold a finite amount of information, proportional to its surface area. If you tried to simulate the entire universe, every particle, every field, every fluctuation, you'd need to store that information somewhere. But where? Inside the universe? That's like trying to fit a container inside itself. You'll always come up short. This puts a fundamental limit on how much of the universe can be simulated from inside the universe. You can model parts of it. You can build approximate simulations. But a full one-to-one replica? It's not just difficult. It's physically impossible unless you're okay with leaving parts out, simplifying, or using statistical tricks. But what about quantum computers? They're different. They don't simulate quantum systems the same way classical computers do. They are quantum systems. That gives them a kind of native compatibility. You can represent certain interactions more efficiently, process entanglement more naturally, and perform computations that would take classical systems thousands of years. But they're still bound by the same laws. A quantum computer with 100 qubits can simulate certain quantum systems with 100 particles. But simulating every qubit in the universe? That would require a quantum computer as large and complex as the universe itself. So again, we hit the same limit. A system cannot perfectly contain a model of itself. There's always a boundary you can't cross. Still, that doesn't make the effort meaningless. You don't need a perfect simulation to learn something useful. That's what science does all the time. It models slices of reality. When we study planetary motion, we ignore friction. When we study thermodynamics, we simplify molecules into particles. In quantum physics, we use ideal systems. Two particles here, a wave function there. Not because they're perfect models, but because they help us understand the rules. So if the universe is a quantum computer, and we're part of it, then maybe our job isn't to simulate the whole thing. Maybe it's to identify patterns, to isolate small, repeatable structures, to reverse engineer the logic in pieces. We don't need to build a second universe to understand the first. We just need to trace the pathways of information step by step and figure out what kinds of patterns are stable, what kinds lead to collapse, and what kinds produce the complexity we see all around us. That might sound modest, but it's powerful. Consider this. We already know that parts of the universe are computationally irreducible. That means there's no shortcut, no trick to jump ahead. You have to let the process run. That's why weather is hard to predict. That's why the future of chaotic systems remains out of reach. If the universe really is running as a computation, then understanding its future doesn't mean solving an equation. It means understanding the computation itself, how input becomes output, and how that process evolves. Could we ever simulate that completely? Probably not. But that doesn't mean we're stuck. In fact, it's likely that partial simulations, small, focused quantum models, will be our most powerful tools. They already are. Researchers are using quantum processes to simulate chemical reactions, condensed matter systems, and even simplified black holes. These aren't toys. They're windows into the underlying rules. And there's one more angle worth considering. If we can't simulate the universe completely, can the universe simulate us? In a strange twist, it already does. Every particle interaction, every biological process, every neural signal, they all play out according to the rules of quantum information. We are already being simulated in a sense, not artificially, but as part of the computation itself. We are sub-processes in the larger system, running, updating, reacting, reflecting. So maybe the goal isn't to replicate the universe. Maybe it's to recognize that we're already embedded in it, not just as observers, but as active computations, as structures that can study the rules, adapt to them, and even push them through science, through thought, through questions like this one. If the universe is a quantum computer, then it must obey the same limits as any other system that processes information. And that means it can't compute forever. Not in the same way, not at the same level of complexity. At some point, every computer runs into constraints. Energy runs out, memory fills up. The system reaches a limit, and the process either halts, slows down, or breaks apart. So if the universe is computing its own evolution, what happens when the resources it needs, time, energy, order, start running low? This isn't a philosophical question. It's already written into the laws of thermodynamics. The second law states that entropy tends to increase over time. In the language of information, that means usable energy is gradually converted into noise. Systems move from structure to randomness. Order decays. And once everything is maximally entropic, nothing meaningful can happen. No more gradients, no more contrast, no more flow. From the computational perspective, this is terrifyingly simple. Without usable energy, computation stops. Right now, stars shine because they have fuel. Planets orbit because of stored kinetic energy. Living systems function because they convert chemical energy into structure and thought. But all of these processes are part of a one-way path. Gradually, energy is being spread out, locked away in unusable forms, lost to the background. Physicists call the likely end state of the universe the heat death, a time when everything is so spread out, so uniform, that no work can be done. No stars, no structure, no computation, just particles drifting in cold silence. From a classical perspective, that's already bleak. But from a computational one, it's worse. It means the system will still exist, but won't be doing anything. A frozen machine, still technically on, but with nothing left to calculate. This raises questions we usually avoid. If the universe is a quantum computer, then is it already degrading? Are we living in a particularly active phase? A temporary spike in complexity before a long descent into inactivity? Cosmologists have tried to estimate how much time the universe has left before this computational quiet takes over. Some suggest trillions of years before stars burn out completely. Others go further, imagining a timescale so vast that even black holes will evaporate, leaving behind nothing but radiation. But even before that, the rate of computation, the generation of new structures, events, and the outcomes will begin to drop. The system will slow down. This doesn't mean things will shut off in a dramatic way. It means change will stop being interesting. If there are no more energy gradients, then nothing can evolve. Without contrast, there's no computation, just repetition or stasis, a loop with no feedback. That brings us to another concern. What happens to information? Quantum mechanics tells us that information can't be destroyed, only transformed. So, if all the computation slows to a crawl and energy disperses, where does all that stored information go? Is it locked in frozen particles, encoded in the subtle structure of empty space? Some physicists believe it might still be preserved in principle, even if it's inaccessible. The information wouldn't vanish. It would just become unreachable, like data on a drive with no power. Still there, still part of the system, but inert, unreadable, trapped. Others suggest the information might loop, not in a science fiction sense, but in a thermodynamic one. That given infinite time, even the smallest random fluctuation might eventually recreate complexity. This is where the concept of Boltzmann brains comes in. Hypothetical observers that spontaneously form out of chaos, briefly experience awareness, and then vanish again. It's not comforting. In fact, it points to a universe where meaning emerges rarely, unpredictably, and briefly before being swallowed again by noise. Another implication is structural. In digital systems, when memory is full or a process fails, you sometimes get a crash, a breakdown, a halt, or a forced reset. Could something like that happen at cosmic scales? Is there any scenario where the computation doesn't just fade, but ends abruptly? That's harder to answer. We don't know if the universe has any built-in mechanisms for halting itself. The expansion of space appears to be accelerating, not slowing. If that continues, the universe won't collapse. It'll stretch into cold emptiness. But if something about the computation changes, say a phase transition in the vacuum, or a breakdown of known physical laws, the system could undergo a radical change, a reboot, a shift to a new computational mode with new rules, new physics, a clean slate. This possibility, sometimes called vacuum decay, is still speculative, but it's a reminder that the rules we observe now might not last forever. If the laws of physics are expressions of a computation, and the parameters of that computation shift, then reality as we know it could dissolve, not because of violence or destruction, but because the system no longer supports the logic that defines our version of reality. And if that's true, then what we call existence might not have a firm edge. It could be a phase in an endless process of information being reorganized in different forms. Structure giving way to noise, noise giving birth to structure again and again. So the dark implication isn't just that the computation could stop. It's that it might keep going without us. Without thought, without memory, without complexity. Just pure information, unfolding meaninglessly, like a loop no one can watch. A process that persists because nothing prevents it. Not because anything drives it forward, and yet, even that has weight. Because right now, in this moment, in this thin slice of time, the computation is active. The gradients are still here. Structure is still forming. Complexity still emerges. The universe is still doing something. And that's the piece we tend to miss. If the quantum universe really is a computation, then meaning isn't something built in. It's something that arises during the rare phases when structure exists, like now. It may not last forever, but for now, it's real. And that might be enough. After all the theories, all the analogies, all the careful modeling, we're left with a question that doesn't get asked often enough. Is this it? Not in the pessimistic sense, but in a serious one. If we've come this far, if we've stripped reality down to quantum logic, to informational flow, to the rules that make the rules, then how much deeper can we actually go? How much more fundamental can our questions be before they stop being answerable? Thinking of the universe as a quantum computer offers clarity. It gives us a consistent picture, one where everything from the smallest particle to the largest structure is made of the same basic stuff, information processed according to quantum laws. It explains the strange behavior we see in nature, the probabilistic outcomes, the entanglement, the interference patterns, the limitations on measurement. These aren't glitches. They're features of the system. They're what you'd expect from a computation unfolding at quantum scale. And unlike older metaphors, this one doesn't treat us like outsiders. We're not observers watching a system from a distance. We are within it. Sub-processes in the very logic we're trying to decode. That makes things personal, not in a mystical way, but in a structural one. We're part of the computation trying to understand itself. So maybe this is the right lens. Not the final truth, but the clearest frame we've found so far. It connects the dots between physics, computation, complexity, and experience. And it does so without inventing new forces or dimensions or magic. It just says, what if everything is information, and everything evolves by the rules that information follows? But this also sets a boundary, because if the universe is a computation, then there are things we may never know. Not because we're not clever enough, but because some things are unsolvable from inside the system. Some problems in mathematics have no solutions. Some questions in computing are undecidable. There are limits, and we already know they exist. So, we might never answer what started the computation, or what, if anything, lies beyond it, or whether there's a deeper substrate beneath quantum information itself. We might reach the bottom of the stack and realize the last layer is logic, not substance, not meaning, just structure. And maybe that's fine. Maybe asking for more than that is a leftover habit. The hope that there's always another explanation, another layer, another deeper reason. But the quantum computer view doesn't offer comfort. It offers coherence. It doesn't explain why we're here, but it does explain how the system behaves while we are. And maybe that's what makes it unsettling. There's no grand narrative, no built-in purpose, just a set of rules, evolving states, and the rare emergence of complexity along the way. Still, within that process, there's something undeniably strange. A brief phase on one planet, in one corner of the system, where particles arranged themselves in such a way that they became aware of the computation. They began to study it, question it, simulate parts of it, talk about it. And that's where we are right now. We are quantum systems shaped by information, reflecting on the process that shaped us, using the very tools given to us by the system to ask what the system is. That might not be the answer we hoped for, but it might be the most honest one we ever get.